Hello, my name is Carlos Silva Santos and I'm here to introduce to you with great pleasure the new Windie CFD code for the analysis of wind flows over complex sites especially, which is part now of the portfolio of Megajoule Inovação's technical capabilities. Windie is a code that is the result of the collaboration between Megajoule Inovação and the ISEP Porto Institute of Engineering, and it's the brainchild of Fernando Aristides Castro, professor at ISEP, and has counted with the collaboration as well of myself, Carlos Silva Santos, and Professor Lopes da Costa for its creation. There are a number of publications by the authors of the Windie code, which you can consult. I'll give you a full list at the end. Windie is a full Navier-Stokes equation solver using a RANS model, uses terrain following meshes, it can perform time-dependent simulations, and it's parallelized. Typically, you would perform a simulation, a study of your wind farm by performing individual simulations using idealized boundary conditions, and you would obtain results in terms of wind velocity, turbulence intensity, flow inclination, and shear factor. In terms of time-dependent simulations, you would be able to extract oscillating behavior and results varying in time to detect certain phenomena associated, for example, with pulsating recirculation regions or gravity waves, which are often of interest in the analysis of wind farms and wind turbine behavior. In terms of turbulence modeling, Windie has quite a collection of turbulence models which can help in the analysis of the wind flow and in the reliability of its results. It has perhaps the most advanced forest canopy model available, with vertical tree density description, and especially, and I will focus our presentation on this aspect, it has the capability of being coupled, strongly coupled with mesoscale models. In this way we can obtain fast and reliable characterizations of regional wind patterns from the mesoscale results, including thermal information, and at the same time from the microscale capture with an advanced CFD code the effects due to the topography and the terrain cover. When coupled with mesoscale models, Windie also gains the capability of modeling temperature-related effects, such as stratification, and it includes now a potential temperature equation to do so. It also includes in its modeling capabilities Coriolis and buoyancy terms. Some quick results. We have two simulations here in terms of that are time dependent. They are fed with results from the mesoscale simulation using the WRF model in this case, and typically you extract WRF results at every 20 minutes and you interpolate them in time and in space to your boundary conditions of your Windie domain. This way you obtain two time series here, shown here, one for the WRF result, for the WRF simulation in red, and then two others, in fact there are three simulations, two others from Windie simulations using two different turbulence models, which can be compared with the measurements shown in black. In terms of mean wind speed, you can see that the WRF model has an underprediction of 30%, compared to an underprediction for Windie of 3% only. This is another period. The first one was in April, this one is in November, a different stratification regime. and you have for Wharf an error of minus 26%, whilst Windie goes down to minus 3% as well. So clearly the Windie code is capable of capturing the complex phenomena of atmospheric boundary flows in complex terrain. However, those time-dependent simulations are quite expensive computationally, especially if you want to perform a year-long simulation to have a complete picture of your wind farm using mesoscale, microscale coupling. So we have devised a new approach by which we extract boundary conditions from average Whorf results for each wind direction. We perform the Whorf mesoscale simulation for a year or more than a year, multi-year. We extract Whorf fields from this simulation whenever a wind direction falls within a certain sector at a reference station that we choose. Then we average these sets of fields into a single three-dimensional wind for that wind direction. The result are very different boundary conditions for the Windie code. Instead of the idealized log profiles that are used by almost all CFD codes available, we have very different conditions at the several boundaries. There is no longer a single inlet boundary, for example. The wind can come from many directions. For example, in terms of the profiles at a point on the northern boundary, we have in red the idealized profiles in terms of velocity and direction, and in blue the ones extracted from this average Whorf results. In terms of flow patterns of the CFD solution, you can see on the left from the traditional approach typical and fairly steady flow patterns for the idealized conditions, and whilst using the Whorf data you have quite a different picture, even though at the reference station, in this case is the second station from the bottom, from the south, you have the same wind direction on site. In terms of results, we are assessing results here in terms of relative speed up between the three other met masts and the reference station. You have considerable errors using the traditional approach, which are confirmed not only in traditional Windie, so to speak, and other CFD codes in the market. You have errors in the level of 73% for each station. So this is a mean absolute error. Whilst in Windie, these errors go down to 3% and the prediction of the speedups is almost exact. Using 330 degrees, so a different direction for the same site, which is a site of moderate complexity, or moderate to large complexity, you have a similar reduction in the mean absolute error using the traditional approach and this new coupled approach. So the applications of Windie, even though we are still collecting other results and performing a number of validations, hopefully culminating in an article in a major scientific journal, we think it can be, the results are very promising, and Windie can be profitably used at several stages in the project, from preliminary studies in met mast siting to the assessment of problems in existing wind farms and the causes of these problems, to the areas of site and resource assessment, and whenever you have complex features in your site, be it the topography itself or other obstacles and terrain cover that can cause problems to the functioning of wind farm turbines. Here is a list finally of publications from the authors of the code. I would like to thank you for your attention and leave you with our contacts and the assurance that we would be more than happy to answer any questions or to arrange to do a personal presentation to you, and so please do not hesitate to call us. Thank you very much.